Hey class, this is chapter 4. You're going to like chapter 4 because, believe it or not, we have done most of the stuff in the beginning here for chapter 4 already. We did it as part of chapter 3. That's how I teach it. So this is not going to be all new stuff for you. It's actually going to be a lot of review from what we did in chapter 3, and maybe about 20% of that is going to be actually new stuff or new concepts. Now, I still might be using some of the same terms, maybe different terms from what we did chapter 3, but the concepts are the same. Let me show you what I mean by that. Okay, so this is solution chemistry. Okay, so what are solutions? Solutions are when you take something, some type of compound, and of course you have to then dump it into water. And when you dump it into water, the water is the solvent or the thing that dissolves or the thing that there is more of. And then the solute then is whatever you dumped in water to give you a solution. So it's a homogeneous mixture. That's what a solution is. You can use solution. It doesn't just have to be for when you have a liquid solution for water with something. You can also have a gaseous solution, such as like air is a gaseous solution. Most of it's nitrogen, N2, 78%, 21% is oxygen, and so on. And then there's a whole 1% of water vapor, carbon dioxide, argon, neon, and a whole bunch of other stuff. So that is also considered a solution. You can have a solution of solid stuff. That would be like alloys with metals. Those are also a solution. They're a homogeneous mixture of two or more pure substances. So let's keep going here. So dissociation. So here's what happens. When you take water and you mix it with something solid like sodium chloride, right? What you get is you still get the water, obviously. The water sticks around, but the sodium chloride changes form. And the reason why it does that is because of the special nature of the water molecule. As it turns out, water is very specific and very different from other compounds that are similar to it. Something like what compound would be similar to it? Well, if you take a look at the periodic table, you'll notice oxygen in the upper right-hand corner, fluorine in the upper right-hand corner, and then around oxygen, you will see sulfur down below, Te below that, and then it just, Se and then Te. So what happens is we know that groups or families, the elements tend to have similar properties, but oxygen is so electronegative, it pulls on other elements' electrons so much so that its properties are different from sulfur and from selenium and from tellurium. So that's why water is so different, and that's why water is so necessary for us, because it has special properties. Something we'll talk about a lot more in AP chemistry if you choose to take that class, which I hope you do. So what happens here is water will pull apart sodium and chlorine from each other. Down here you can see the crystals of sodium and chlorine, right, as they are positive and negative, and then as water floats in to meet up with the sodium chloride crystals, there's a positive end of water and there's a negative end of water, and they start to attack the actual atoms and pull them off. And when that happens, then you get a sodium atom ion, not an atom. You get a sodium ion floating freely, okay, that has been pulled off by water, and you get chlorine ions that are floating freely within water, because water's positive end had pulled off the chlorine, and the negative end has pulled off the sodium. And that's how dissolution or dissociation works. Okay, so when something gets dissolved, it dissociates or it separates into its ions. Okay, now most metal, non-metal compounds will do this. So most ionic compounds will separate into their ions, which is kind of why they're called ionic compounds. So let's keep moving here. So I don't want to take this, I don't want this to take too long. When you have a lot of ions in a solution, then what you have is something called an electrolyte. So there are three classes of electrolytes. There are strong electrolytes, which have a lot of ions. I'll write that here. Lots of ions. Okay. There are weak electrolytes, and I'll explain more about that. Those are very specific. And then there are non-electrolytes. Of course, if you have an electrolyte, you can also have a non-electrolyte. And a non-electrolyte is something that does not have ions but still dissolves in water. An excellent, like the best example of a non-electrolyte would of course be something like sugar. You know that sugar, if you don't know this, let me think here. One of the sugars is C6H12O6, glucose, I believe. Some of them, like sucrose, is C12H22O11. These are all different types of sugars, and all of them dissolve in water, but none of them produce ions. So this molecule of C12H22O11 separates from the other molecules of the same formula and float freely, but not because they're separating into ions at all, because these are all non-metals, and this is a molecular compound, as opposed to something like sodium chloride, which has a very strong ionic property, which means it separates into its plus and minus properties. Okay, so let's keep moving here. So electrolytes and non-electrolytes. So what happens is we have the electrolytes that dissolve, of course, when there is ions in a charge, like soluble ionic compounds tend to be electrolytes. They can conduct electricity, just like a wire can, believe it or not. Electricity is just simply the movement of electrons. And when there are ions in a solution, there are electrons available to be moved, which is why like salt water conducts electricity a lot better than pure water does. And we'll talk more about that. So when we have a molecular compound, they tend to be non-electrolytes, okay, except for acids or bases. Acids and bases are very specific and very situational. They're very special because the positive part for acids is H, and H is very small with a positive charge, which means that it has like a very metal-like situation. So when you see something like HCl, that actually breaks up 100% of the time, and we'll talk about this when we get to acids and bases, 100% of the time into H plus and Cl minus, then producing ions, which is why strong acids are a strong electrolyte, and strong bases are also. But that one's kind of obvious because strong bases, when they break up into a metal and hydroxide ion. And we know that ionic compounds, which bases are, and obviously so are acids, but acids are a little bit different because there's no metal in them, but bases have a metal. Okay, moving on. So electrolytes. Strong electrolytes dissociate completely when dissolved in water. The weak electrolyte only dissociates partially. So here's what that means. Sometimes you can have something called like a weak acid. And we have many weak acids, and a weak acid would break up like this. But whereas a strong acid would break up 100% of the time, this one actually only breaks up a very small percentage of the time. 1.7% of the time does this actually separate. So that means we have much less ions floating around than we do the actual molecule of the weak acid. That's how we explain what a weak electrolyte is. So a weak electrolyte is when something only partially dissolves in water, and it's got to dissolve to a very small amount. So strong acids are, of course, strong electrolytes, and so are strong bases. Let's keep going here. Strong bases. So what are the strong bases then? So, let me go back. So what are strong acids? You guys know that strong acids, I've said this already for HCl, it's a very popular one, so everybody knows that one. Also HBr, hydrobromic acid, and then we complete that with the hydroiodic acid. Those three are all strong. There's one that's missing here, of course, and that would be HF. HF is not a strong acid. It's a very dangerous acid, but for a different reason. This is a weak acid, though not a strong acid, as you might suspect. So over here, we have other strong acids, but these have the polyatomic ions. The polyatomic ion for this one's nitrate, so this is nitric acid. You've heard of that before. Okay, this one is chloric acid when we have chlorate. There's another one that is perchloric acid. This is the strongest acid that does not have organic material attached to it. So this right here is the strongest acid. This is perchloric acid. And then, of course, we have the single most produced chemical in the country, which is sulfuric acid, H2SO4. Okay, so these are the 7 strong acids. Please write them down. Please know that they're the strong acids, because anything else that I write down with H in front of it is not a strong acid. It's a weak acid. There are only 7 strong acids, so it really does you well to know these so that when we move forward, we know what a strong acid, strong base reaction looks like, because it has to be one of these 7 that's in the reaction then. Okay, so here's the list again, and here's the names of them in case you didn't catch it when I was going through that. So here's the strong electrolyte. This is strong acids and strong bases. So all of group metal 1 with hydroxide. So that means lithium hydroxide. It means sodium hydroxide, right? It means potassium hydroxide, rubidium hydroxide, and what's the other one? Cesium hydroxide. So these are all strong bases. So there's 1, 2, 3, 4, 5 of those, and then we have 8 because we have 3 from the bottom 3 of the 2A group, where it's calcium, strontium, and barium. Those are the 3 that also produce strong bases. Okay, it's not as important to know these, I'm sorry to say, because the bases don't affect nearly as many things as the acids do. So the strong acids is by far the more important list to know or to recognize. Let's move on. So what else do we have for strong electrolytes? They are the soluble ionic compounds, such as NaCl. We keep using that because it's common to everybody. And there are some things that always produce soluble compounds, such as anything that's a nitrate. Okay, anything that's attached to nitrate is soluble, like 100% soluble. Okay, acetates are the same way. So acetates are anything that like have the C2H3O2. Chlorides are mostly soluble. There's a couple other ones. Oh, chlorates are another ones who are always soluble. So if you see anything with a ClO3, that's a little bit less common, but basically any of these 3 are soluble. Here's another thing that's always soluble. Remember we talked about alkali metals? All of group 1 is completely soluble. These are all soluble compounds. So if you see anything that has sodium in it, you know it's going to dissolve well in water. Okay, it doesn't matter what follows sodium. It can be any of those things that we see that are like not very soluble. Okay, so hydroxides tend to be not soluble unless it's group 1 or group 2. And when anything is in group 1 attached to sodium, then of course it's going to be soluble. Okay, so those are some like constants that are always happening. It's always dissolvable. Here's another list, but I don't want you to memorize this list. This is not worth memorizing. These are like based on the solubility rules, and you actually have a list of the solubility rules. They're below the solubility table that we had for chapter 3. Wow, I just talked really quick there. I'm trying not to. You pause this and take notes and make sure you know what's going on. So precipitation reaction. This is the same reaction that we had before. All of this that we're going to talk about now are double displacement reactions. You know what those are because in case you're not sure, that would be sheet number 7 from our notes from last chapter. This is all based on chapter 3's notes on double displacement reactions. Okay, so they're called metathesis reactions because that means exchange. That is the same thing as a double displacement reaction. Do not be confused. We start with the same thing here that we did before. We do A, B, C, and D, and then when I switch them over here, it's A and D, and it's C and B, and look what happens on the other side. Oh, okay, so there they're just showing the A and the D. And then here, we got the same thing, A, D, C, and B, just like that. We've done this before. You guys know what this is. I don't have to spend a lot of time on this. These are switching up into ions. Look what's happening here, though. We get a solid. Just like when we use the solubility chart, that's where the solid comes from. We check the chart. This tells us it's a solid. Now we're going to move into something else called, well, this is called solution chemistry because these species are present in a reaction mixture as aqueous, usually, which means that they're ions. If we are to understand the reactivity, we must be aware of just what is changing during the course of the reaction. That's a good statement. That means very little. So let's move on here. So notice that everything that has AQ after them, this is a molecular equation, by the way. The molecular equation is exactly the same equation that we've been working with the whole time. So don't be confused about this. Don't overthink it. The new part is when we turn them into ions. Anything, let me back up again, anything that has, and I'm going to erase the one with the solid, anything that has an AQ after it can be broken up into ions. That means that the Ag here has a plus ion and the NO3 here has a minus ion. And then we continue on with the K with a plus and the Cl with a minus. That's all the next slide is doing. Over here, this one has a solid, so AgCl is solid. That does not get broken up into ion because of that. Okay, and then we continue on with the plus and the NO3 as a minus, like that. So we break up everything that has an AQ. And then we move on. When you see this, and you see all of these things spelled out, and the solid is left behind unchanged, that means everything floats around here. The Ag plus floats around, the NO3 floats around, the Cl minus floats around, the K plus floats around. Now I want you to see what happens when this is called, this right here is called an ionic equation, but this is not a very useful equation. All we did was make busy work by breaking them up into the ions. Here's where it gets important. Notice that there are ions on both sides of the equation that have not changed. The silver changes because it changes into a solid. The chlorine changes because it changes into a solid. The rest of them float. The NO3 and the K+, they float around and don't do anything. These are called spectator ions. They'll say that in the next or one or two more slides coming down. So we get rid of the spectator ions, and what we have left are the things that actually change in the reaction. This is called a net ionic equation simply because the net means that we get rid of the stuff we don't need. Okay, just like when you have a gross income and you have a net income is after we take away the taxes, and a net ionic equation is after we take away the spectator ions, or the ones that float around and do nothing. Okay, so we'll talk way more about the spectator ions, what is and what's not. Okay, so notice we go back to here. It says those things that didn't change and were deleted from the net ionic equation are called spectator ions. Okay, that means they are watching the reaction but did not actually take part in the reaction. And those things that took part in the reaction are the things that actually changed, which would be the silver chloride on the right-hand side. Okay, so I feel like I'm repeating myself now. So writing a net ionic equation, I'm going to give you a paper that we are going to do. I'm going to show how to do the net ionic equation. I'm going to ask you to do it. It's going to be an assignment, and I'm going to have a screencast with it. So I'm going to skip this part and continue on. Okay. Actually, I think that's it for 4.1 and 4.2. Thank you guys for paying attention. Take the notes, and I'll be talking more about net ionic equations.